All right, this is Pre-Calculus B, Unit 2, Lesson 11, Trigonometric Functions Review. You do have a portfolio in this lesson, so that's a separate video and so forth. I thought I'd point out something that the lesson brought up. It was really kind of interesting. Being a guitarist and a musician, I'm fascinated by the mathematics of music. And they introduced the concepts that actually lead to a whole field of study called signal processing. And it's dominated by a concept called Fourier transformations, F-O-U-R-I-E-R, Fourier. And I want to introduce some of the ideas here. If you're into music, you know that the orchestra tunes itself to concert A. A is 440 hertz, and let's go to a screen to write on here. So A, and then on the piano keyboard it's called A4 because it's in the 4th octave. A4 is 440 hertz. Okay, a hertz is 1 cycle per second, so this is 440 cycles per second. If I take the and invert that, we get something called the period, how many pulses, or the time it takes for one pulse. So 1 over 440 seconds is the period it takes for one pulse of sound at 440 hertz. Okay? We can model this with a sinusoidal function. A pure sinusoidal signal would at this frequency would generate that sound, and I don't have a signal processor to generate it, but basically we would say sine x, but I would have this factor where I change the period here. Remember, 2 pi changes the period of sine to 1, right? And now if I divide by 1 over 440, you can see the signal. Now it's very fast, so this particular scale is not going to work. So I'm going to change the scale on the x-axis to 5 thousandths and 0.05. Actually, that's not enough here. Let's try 10 thousandths. There. Well, that's too much. Oh, it would help if I did negative. There we go. There we go. All right. And so now we can see, right? And in fact, if I want to make it even more obvious, let's change the y-axis to go from -2 to 2. -2 to 2. There we go. All right. And I'm going to fiddle with this just a little bit more to get a better picture. X-axis, let's do -0.004. Negative to 0.004. Let's try 3. I want to spread it out just a little bit. Okay, there we go. All right, so a good sinusoidal signal. Okay, now that's kind of ugly to type, so I'm gonna type in a constant here. I'm gonna say k equals 2 pi over 1 over 440, which of course is 880 pi. But I'm gonna leave it like this so that when the meaning is clear. And I'm going to insert k. Okay. All right. Now, what happens? The lesson introduced something called the harmonic series. If I double the frequency, I get in music we get an octave, right? So if I double the frequency, I get sine 2k. Okay. Or sine 2kx. Okay, and notice now it's double the frequency, but I want you to notice the points that are the same. All the places where the original function were 0 are still 0 in the new function. Okay, still 0 in the new function, still 0 in the new function. Okay, if I add in this, that's known as the second harmonic. If I add in the third harmonic, in which the period is tripled, we get sine 3kx. Okay, and again, notice those 0 points here on the original function are still preserved. It's still 0, all in the same places. Okay, so what signal processing does is it says let's take and add all these multiples, all these harmonically coherent signals. Let's combine them by addition. Okay, so let's go back to the original one here, and let's add sine kx plus sine 2kx plus sine 3kx, and you can see the signal changes shape as we go, plus sine 4kx, and you can imagine adding a whole bunch of these here. Let's change the y scale here. There we go. Okay, you can add a whole bunch of these and keep going, and you can see the signal changes, but the base frequency stays the same. Those 0 points are right here and right here. Actually, so the 0 there, it's a cyclical thing that preserves the original zeros. I think the original 0 was right here and right here. Yeah. Okay. And actually, no, right here. Just looking at where the midpoint is. Okay, yeah, something like that. Okay, now where it really gets interesting is if I start putting multipliers in front of each of these, A, B, C, and D. Okay. And I'm going to add sliders for these, A, B, C, and D. Right now they're all 1, so we got our base signal. If I start modifying the coefficients on each of these terms, I can change the shape of the signal and the repetitive signal. So that's A0, right? I can fiddle with these and end up with all kinds of different shapes. Now, if I try to match existing frequencies or existing signals, I can recreate all kinds of things. These are called Fourier series. And using or writing a signal that matches with as a sum of these is called a Fourier transformation. And computers work really well. They use a field called fast Fourier transformations to model signals with the sum of these sinusoidal or cosinal functions. And that allows you to do all kinds of mathematics with it. Some examples that apply to music is if I can take and sample, we call it signal sampling. I can sample the sound from a really high quality Stradivarius violin, have someone play notes, and I can sample that sound. I can then use mathematics to match that signal mathematically, and I can cause a computer to generate that signal at will. And so through sampling, I can create synthesizers that create very realistic sounds. Now, of course, there's other problems like attack and decay that affect the quality of sound, but I can generate very real sounding synthetic sounds with this method. Not to mention it's got applications in power management, because our power grid is on a 60 cycle or 60 hertz alternating current, and we have signals from space that we try to match and understand. So whole fields of mathematics. I'll go ahead and post a Khan Academy video. He has a whole series on Fourier transformations. Now, it does take calculus, but the initial lessons don't. And so really kind of fascinating stuff.